Welcome back. This is Mr. Greenstein's Geometry, and we're in the middle of section 6.1, perpendicular and angle bisectors. So the first point we want to make here is, what is the distance from a point to a line? If I just pick, if I have a point P that's away from a line, then I could just draw a distance like that. But that's not really what the distance is. The distance is a very specific line, not just any old line that I pick. The line that is the distance is the length of the perpendicular segment from the point to the line. It has to be to the perpendicular. And you can see that this is actually the shortest distance. So the shortest distance between a point and a line is the distance, what we call the distance between the two. An angle bisector is a ray that divides an angle into two congruent adjacent angles. So the ray here is AD, and it breaks up this angle BAC into two congruent angles, 1 and 2. That's an angle bisector. The distance from D to C is the distance from this point D to this side here is this perpendicular distance. It's not the straight distance. A lot of times people will just draw a straight distance like that, but that is not the distance we're talking about, because that's not the shortest distance between D and that side of the angle. The angle bisector theorem says that if a point lies on the bisector of an angle, then it is equidistant from the two sides of the angle. So from D to B, there's a perpendicular distance, and D to C, there's a perpendicular distance. And these two distances are going to be the same, so we can mark those. Those are going to be congruent. The converse of the angle bisector theorem says that if a point is interior to an angle and it's equidistant, so that we know that the distance from there to each side of the angle is the same, then this point lies on the perpendicular, or on the angle bisector. So that's the converse of the angle bisector theorem. Let's actually use this in solving these problems. I have this distance here from J to G, that side, and to that side, it's the same. Therefore, this ray and J has to lie on the angle bisector. So to get GFJ, since it's an angle bisector, that means that 42 degrees has to be the same over here. And to figure out what GF is, well, this is a right triangle, so we just use Pythagorean theorem, and I'll leave that up to you to compute what GF is. Down at the bottom, I have an angle bisector, and since S is on that angle bisector, we know by the theorem that the distance from here to here is going to be the same as from here to here. So we can just make 5x equal to 6x minus 5. And when we do that, we find that x is equal to 5. And PS, well, PS is going to be 5 times 5, which is 25. Write an equation of the perpendicular bisector. So, writing an equation of the perpendicular bisector of these 2 points, if I graph these 2 points, -2, 3, so there's P, and Q is 4, 1, and there's, I'm just going to sketch that. Then write an equation of the perpendicular bisector. What we want is we want the line, and I'll just sketch it here, that goes through the center of that segment and is perpendicular to it. So to come up with that, I have to get the slope of PQ. And the slope of PQ is equal to -1/3. The slope of the perpendicular is going to be the negative inverse of that, which is just 3. And then the point that's going to be on the line is going to be this midpoint here. So the midpoint has to be calculated, and the midpoint is going to be 1, 2. So we're using the midpoint formula to come up with this. And once we have that, then we can write our equation. So we use the point slope form. Y minus 2 is equal to 3 times the quantity x minus 1. And that is our equation for the perpendicular bisector. We'll continue this conversation the next day in class.